My name is Eric Severson. I'm a PhD candidate at the University of Minnesota, advised by Ned Mohan. I'm co-advised by Robert Nilsson at the Norwegian University of Science and Technology. I'm now going to demonstrate a prototype of my dissertation research on the bearingless AC homopolar motor. The bearingless AC homopolar motor is on the right side, and the drive is on the left side. Zooming in, we see that the prototype consists of a rotor and a stator housing. On the bottom of the rotor is a permanent magnet bearing, which is used for axial levitation. The machine is currently powered down, which means that the rotor is not centered and is free to move about. On the top and the bottom, we have position sensors. These are eddy current position sensors, which measure the XY displacement of the rotor. That is, the distance between the position sensor head and an aluminum sleeve fixed to the rotor in two planes, top and bottom. These sensors connect to oscillator demodulator boxes at the top, which in turn go to A to D converters for feedback. All of these connections are end connections of the winding. This is a special winding which is able to produce radial forces and torque using the same coils. These boards connect to the wires going into the end connections of the machine. They measure the current for feedback. These boards here are based on silicon carbide MOSFETs. They are the power electronics that apply voltages to the machine's windings. All of this connects to a control card, which reads in A to D signals from the various sensors and outputs PWM signals to the electronics. The control card has a DSP and FPGA for control. We'll now turn the machine on, and the rotor will center itself. The rotor is now centered and free to rotate. There is no friction as it is completely magnetically levitated. However, there is still windage loss, so the rotor will eventually slow down. There is both windage loss and magnetic loss. The rotor can be pulled side to side, and the control will react. There is not so much radial force as to prevent you from fully displacing the rotor. I will now tell the controller to spin the rotor up to 1000 RPM. You can see the rotor has started rotating. As the speed increases, you will hear it pass through a critical speed. The test stand will vibrate. The rotor has now reached 1000 RPM.